Imagine a dead star the size of a city, spinning 700 times every single second, with a magnetic field a trillion times stronger than Earth's. That's a pulsar. And as of 2026, we've found over 3,000 of them scattered across our galaxy. These things are so bizarre that when we first discovered them, scientists genuinely thought they might be signals from alien civilizations. I'm not joking. They literally called the first one LGM1, Little Green Men 1. By the end of this video, you're going to understand exactly what a pulsar is, how it forms, and why it's one of the most extreme physics laboratories in the entire universe. Let's dive in. First, let's get the basic definition out of the way. A pulsar is a type of neutron star. It's the ultra-dense core left behind after a massive star explodes in a supernova. But here's what makes it a pulsar specifically. It's spinning incredibly fast, and it's shooting beams of radiation out from its magnetic poles. As it spins, those beams sweep across space like a lighthouse. When those beams happen to point toward Earth, we detect a pulse. That's why we call them pulsars. They're not actually pulsing. They're just spinning so fast that we see regular flashes of radiation. Now let me take you back to 1967. A graduate student named Jocelyn Bell Burnell was analyzing radio telescope data at Cambridge University. She noticed something weird, a signal that pulsed every 1.337 seconds. Perfectly regular. Nothing natural should pulse that perfectly. Stars flicker. Galaxies don't have a rhythm. But this signal was like clockwork. So precise that her supervisor half-seriously suggested it might be an alien beacon. They even nicknamed it LGM1, Little Green Men 1. But then Bell found another pulsing source. And another. And another. All in different parts of the sky. Unless aliens were everywhere and all trying to contact us at once. This had to be natural. It was the first evidence of neutron stars, objects that had only been theorized decades earlier. Jocelyn Bell Burnell made one of the most important astronomical discoveries of the 20th century. Her supervisor got the Nobel Prize for it. She didn't. That's a whole other story. 3,000 pulsars discovered since then. But what creates these cosmic lighthouses? The answer is one of the most violent events in the universe. A supernova explosion. When a star 8 to 20 times more massive than our sun runs out of fuel, it can no longer support itself against its own gravity. The core collapses in less than a second. In that fraction of a second, the core goes from being thousands of kilometers wide to just 20 kilometers across. That's about the size of a city. The outer layers rebound and explode outward in a supernova. What's left behind is the core, a neutron star. And if the original star was spinning, which all stars do, that rotation speeds up dramatically as the core shrinks. It's the same physics as a figure skater pulling in their arms to spin faster. Except instead of going from 2 rotations per second to 10, the neutron star goes from 1 rotation per month to hundreds of rotations per second. The fastest pulsar we've found as of 2026 spins 716 times per second. That's PSR J1748-2446 AD. At its equator, the surface is moving at about 24% the speed of light. If it spun any faster, it would literally tear itself apart. Even though it's held together by gravity so strong that nothing in the universe binds matter more tightly except a black hole. Speaking of density, a neutron star is so dense that a single teaspoon of its material would weigh about 1 billion tons. That's roughly the weight of Mount Everest. The entire mass of our sun compressed down to the size of Manhattan. The atoms are crushed so tightly that electrons are forced into protons, creating a sea of neutrons. That's why it's called a neutron star. The gravity at the surface is about 200 billion times stronger than Earth's. If you could somehow stand on a neutron star, which you absolutely cannot, you'd be flattened to atomic thickness instantly. The magnetic field is equally insane. Up to 1 trillion times stronger than Earth's magnetic field. Strong enough that it distorts the vacuum of space itself. 1 trillion times Earth's magnetic field. This magnetic field is key to understanding why pulsars pulse. Charged particles near the neutron star get caught in this magnetic field and accelerated to near light speed. When particles accelerate like that, they emit radiation. Lots of it. Radio waves, X-rays, gamma rays. This radiation shoots out along the magnetic poles of the neutron star. Here's the thing. The magnetic poles are not aligned with the rotation axis. Just like Earth's magnetic north isn't exactly at the geographic North Pole. So as the neutron star spins, the beams of radiation sweep around like a lighthouse beam. If Earth happens to be in the path of one of those beams, we see a pulse every time it sweeps past us. The pulse period tells us exactly how fast the neutron star is spinning. Some pulsars spin once every few seconds. Others spin hundreds of times per second. Those fast ones are called millisecond pulsars. The really cool thing is that pulsars are incredibly stable clocks. Some of them keep time more accurately than atomic clocks here on Earth. We're talking precision to within microseconds over years. In 2026, astronomers are using networks of pulsars across the galaxy as giant gravitational wave detectors. It's called pulsar timing arrays, and it's helping us detect gravitational waves from supermassive black holes. More accurate than atomic clocks. Some pulsars are even more bizarre. They're in binary systems with another star. As they orbit each other, they create gravitational waves that carry away energy. The orbit gradually shrinks. We can measure this orbital decay incredibly precisely. It matches Einstein's predictions from general relativity perfectly. The first binary pulsar discovery won the 1993 Nobel Prize because it was the first indirect evidence of gravitational waves. Over billions of years, pulsars slow down. The rotation gradually decreases as they lose energy through radiation. Eventually, they spin so slowly that we can't detect the pulses anymore. They become invisible. But some pulsars get a second life. If they're in a binary system and their companion star starts dumping material onto them, they can spin back up. These are called recycled pulsars or millisecond pulsars. There's even weirder stuff. Magnetars are neutron stars with magnetic fields 1,000 times stronger than regular pulsars. Their magnetic fields are so intense, they cause starquakes on a neutron star's surface. So why should you care about pulsars beyond them just being cool? Because they're natural laboratories for extreme physics. We can't recreate these conditions anywhere on Earth or in any lab. They let us test general relativity in ways we could never do otherwise. They help us understand the behavior of matter at densities we can't achieve. They're gravitational wave detectors scattered across the galaxy. Some scientists have even proposed using pulsar timing for spacecraft navigation. Instead of relying on Earth-based signals, spacecraft could use pulsar signals as a galactic GPS system. As of 2026, new radio telescope arrays like the Square Kilometer Array are coming online. They're going to find thousands more pulsars and let us study them in unprecedented detail. Every pulsar we find adds another data point, another test of physics, another cosmic clock we can use to probe the universe. These dead stars are teaching us more than most living ones ever could. So that's what a pulsar is. The collapsed core of a massive star, spinning hundreds of times per second, with gravity and magnetic fields so extreme they break our everyday understanding of physics. If this video made the universe a little more mind-blowing for you, smash that like button and subscribe to your Space Wizard. We've got more cosmic weirdness coming your way every single week. Out there right now, thousands of dead stars are spinning in the darkness, sending their beams across the galaxy. And now you know exactly what they are.